57, really? That one? And 75? Are we just trying to do them because they're like palindromes of each other? Okay. That's the right word to use there, right? Palindromes. Saying backwards is forward. All right. Don't need those anymore. Oh, I like 57. It's easy. I mean, not for you clearly, but it was easy for me. So we have a object that is oscillating so that it has like a peg out there that's going to stop it. So did we do this one in class before, or did I just do this in, I think I only did this in AP Physics 1. So it's pretty easy to set up. The other piece up here. There, you guys fall asleep, and then we'll start, I have the other piece in the back of me. Is that about the halfway point? Does that look like halfway to you guys? Yeah. All right. So let's do it. Is that how you envision it? Okay. So from this position to this position, that is 1/4 of a period, right? From maximum displacement to equilibrium, 1/4 of a period. We did that whole thing with the spring mass system. Would you agree with that? And then from here to here, also 1/4 of a period. That okay so far? But this period is based on 24 centimeters for the length of the string, and this period is based on 12 centimeters for the length of the string. Aha. So if I want the period for one swing, this is only going to be half of the motion, would you agree? Because this only gets us halfway there, then I have to go back. So whatever we get for the answer here, when I add these two things together, I will double it for the total period. Is that okay? So 1/4 of 2 pi times the square root of L over G, using 12 centimeters for L, plus 1/4 times 2 pi times the square root of L over G, using 24 centimeters for the length, and two of them. Right, that gets me halfway. It wants the period going back too. There's probably another way to do it, but I think you're still going to be doing some combination of this. Any question about that? That's part A. Ready for part B? I know you guys are running off to calculate it, but I don't really care about that part. I want to do the other part. So I'm gonna go ahead and do the other part. You have this written down? It says that the object was pulled 10 degrees back and then released, and asked, what is the pendulum's maximum angle on the right side? Now, this one's, I think this one might catch you by surprise. The pendulum oscillates between gravitational potential energy and kinetic energy, unlike the spring, which oscillates between elastic potential energy and kinetic energy. Everybody understand what I just said? If there's no energy lost, then at this point and at this point, all the energy is in gravitational, which means mgh on the left has to equal mgh on the right. But for a pendulum, h is equal to L times 1 minus cosine theta. Right? We've done this before. Well, that means mg 0.12 times, no, not 0.12. Yeah, 0.12 times 1 minus cosine 10 degrees. That's the left side. All right, the length of the string is 0.12, and the angle that was given was 10 degrees. Does that make sense? So then on the right side, mg, the string length is suddenly changed to 24 centimeters. 1 minus cosine, I don't know. Cancel those mg's, I think. 0.12 divided by 0.24, or 0.24 divided, one way or the other, you're going to get rid of that. So I'm just going to say that this is divide both sides by 0.12, and I get 1 minus cosine 10 degrees equals 2 times 1 minus cosine, I don't know. You're solving for cosine theta at this point, though. So algebra, are you good to algebra on your own? Or would you like me to continue to algebra with all of us? All right, well, you can algebra whenever you're happy to do so. All right, 75, which is the same as 74. So we can do 74 and 75 at the same time. Although I don't think you guys can. Some of you just can't leave that theta unsolved. Watch you pushing all them buttons, trying to get the answer, blah, blah, blah. All right, so both of these problems have you deal with the frequency of oscillation for the object on one spring. They have this setup with K1 and K2, and they have this setup with K1 and K2. But they ask for this frequency in terms of just one spring and the box. K1 in the box, and this one, K2 in the box. They want you to put your answer in terms of the other frequencies. Does that make sense? Or at least, am I defining the question correctly? So this is 1 over 2 pi times the square root of K1 over M. This is 1 over 2 pi times the square root of K2 over M. So follow along with me for just a minute. 2 pi F1 equals square root of K1 over M, and therefore 2 pi F1 squared times M equals K1. You'll understand why I'm doing this in just a minute. I'm not going to go through all the steps again because this is exactly the same to get K2. I agree. This is a snore fest, Tanner. I don't know why I assigned them, except I thought maybe it was actually a better problem than this. I didn't realize when I assigned it that they wanted you to do it in terms of the frequencies, which just makes it like a massive, stupid algebra question. Either way, we proved these in class already. We proved that this one, the frequency, is equal to 1 over 2 pi, bless you, I think, times the square root of K1 plus K2 over M. K1 plus K2 over M. Plug it in, work it out. Do you need me to do it? I won't be happy to do it, but I will do it because it's my job. So that's a yes, do it. Thanks. I won't be happy to do it, but I will do it because it's my job. So thanks. I'm not calling you out. I won't tell the whole class who it was who wants me to do all this stupid math. I'll let them remain anonymous. K1, 2 pi F1 squared plus, M, plus 2 pi F2 squared M all over M. Well, I believe I can factor out an M on the top of this fraction, and therefore, kaboom, I believe I can factor out a 2 pi squared from each term. That might be worth a rewrite. So, over a second, it's not. I can do that too. And the square root of 2 pi squared is still just 2 pi. Ta-da. You're so welcome. But I'm not doing it for the 75. I did this one for 74, but you can do 75, right? We did the 2 springs in a row, didn't we? We did, didn't we? In class? And we found already that the 2 springs in a row thing, this thing, which is like right there, if I get rid of this stuff that's in my way, this sucker was the frequency equaled 1 over 2 pi times the square root of, let me get this right, K1 times K2 over K1 plus K2 times M. I think we did period in the class when I talked about it on Monday, but I just inverted it to put frequency. This one's going to be less fun than the last one, and the last one was not fun anyways. About it in class. So I sent you this. Yeah, I think you should do this one. 3 times the fun. 3.
Are those red bars like the difficulty?
No, they're levels of fun.
Okay. So the more red bars, the more fun.
The more red bars, the more fun.
All right.
So that's why there's all these red bars at the end, because that's where the fun problems are. You know, yeah, I like those. Ooh, I like that solid sphere one too. Ooh, that's a good one. And these are odd numbers, so the answers are in the back. How hard can they be if they give you the answers? I like just saying that. So I sent you all something. And we have the perfect amount of time to talk. Sent is the wrong word. I made it a problem that was due today by 3:30. I did. So I guess we have 15 minutes to do that, but the bell rings in 10. I used to work FRQs with my students in class. I believe FRQ study is important. More importantly, I think that if you're going to improve and want to see what I'm going to give you on a quiz, say tomorrow, it seems relevant for us to have had an opportunity to talk about similar questions and look at some of the ways in which it's going to be on the FRQs. But what I have found is that when I do them, everybody just looks at me cow-eyed and glossed over. If I make it so that you have something you must turn in or else you get no credit, at least you'll write down the stupid answers as we do it. These are classwork. I'm giving you credit for it. You're going to want this credit as we switch over to review. You're going to want to have some buffer in there because review's hard. We just do full exams all the time. So let's get some buffer credit in there. We'll be doing some FRQ buffers like this. I think it's appropriate, but they will always be due by the end of that day. So the idea is we work the problem out. I did have more time in the other classes to work these out because I didn't do as many homework questions. So I don't mind doing the homework, but this is kind of what I want you to work on. I especially want you to have a chance to bustle through this a little bit. A and B are super simple. I'm not going to spend a lot of time on them, and you can see them on your own because you have the capacity to have this problem. It was already sent to you. But if you don't, I will talk about it. You guys see what the picture looks like, right? Go drop a box. It's going to land on a spring. There's information about this. The spring in its relaxed state is 0.45 meters away from the box, which is 2 kilograms. And the spring has a spring constant of 200 newtons per meter. Question A asks, what is the speed of the block at the instant it hits the end of the spring? So we drop the box and the box falls and hits the spring. There's not a lot of work to do there. I'm thinking change of height. Are you thinking change of height? Conservation of energy seems like a quick way to find that answer. Or if you have memorized how fast something has gone when it has fallen some height, like square root of 2gh, you might be able to get to that answer even faster. So I don't want to sweat question A. And I really don't want to sweat question B, even though it's the part that's about simple harmonic motion. Question B asks for the period of simple harmonic motion that ensues. I don't think that's going to be hard either. Do you recognize the kind of oscillator this is? Is it a spring mass oscillator? So do you have perhaps a formula that would tell you the period of oscillation of a spring mass oscillator? Is this a question? Go ahead.
Would gravity affect the period or no?
Well, the easy answer for me to say is no. But the better answer would be for you to set up the net force equation. Show that it can be written as a constant times a displacement, and then find out that that constant ends up just being k by itself. But yeah, it works just fine. All right, look, we have 6 minutes left. I've kind of gone through A and B already, giving you what you have to do. That was because I want you to talk to the people at your table about question C. Please. It's question C that matters. When the box makes it to here, and it just makes it to the spring, it's moving now, right? It's fallen. At this moment, The downward force on the box is mg. What's the upward force on the box from the spring? 0. The spring hasn't compressed yet. And since the upward force from the spring is kx, if x is 0, the spring hasn't started pushing up yet. So advance one instant into the future, and the box has moved down a little bit and pushed on the spring a little bit. Wouldn't you agree that now the spring is pushing up a little bit? But is it slowing the box down yet? Looks like net force is still downwards. The box is still increasing speed because the net force is still downwards. Gravity is greater than the weight. It won't start slowing down until the net force is upwards. So it picks up speed because it keeps pushing down on the spring. The spring keeps pushing up a little more. And until mg equals kx, the box keeps picking up speed. It doesn't stop picking up speed until it reaches equilibrium. I know, that's a tough one. And a lot of people in the room didn't get that. We didn't finish, but I finished it in other classes. I don't care when you turn this in. Turn some of what you've done in today, because I also want you to look at this one, but here's a trick. You have to figure out question D, the maximum compression of the spring. That's when the box has made it to its lowest point here. It has all elastic potential energy here, which equals all the gravitational potential energy here. Here's the problem. This is H for MGH. And this is X for 1/2 kx squared. H equals 0.45 plus X. This one's tough. This one's tough. I did finish this in 4th period, but you guys didn't get all the time, so. Posted one for you to practice tonight that is really similar to one in your homework, but we didn't make it as far. Okay? So, all right, so, the rod is released from rest from the horizontal position shown above. Calculate the linear speed of the bottom end of the rod when the rod passes through the vertical. All right, so the rod began its journey kind of like this. Let me give me just one moment. So the rod begins like that, and then it swings downwards until it's vertical. Okay, so the amount of potential energy it begins with is going to be equal to the amount of kinetic energy it has at the bottom. That's where I want to start. Is there any question about why I'm using conservation of energy here? All right, change of height is the big winner here. And I don't believe we have another method to do this analysis besides conservation of energy. This is probably your only choice. So starting from that vantage point, the reason I can't calculate the linear speed directly, that I have to do angular first, is because I need to factor in the moment of inertia of the object in order to do this. So I can't put this as 1/2 mv squared for the bottom, because that only talks about this piece of mass, and its inertia is different than this piece's inertia. So that's why I have to use the rotational speed here and can't use linear. Somebody in another class asked about that, and I want to make sure I handle that part first. So with that being said, I need the moment of inertia, which was asked about in part A, which you had to get from the parallel axis theorem. And that comes from knowing that we are starting at 1/12 ml squared and shifting a distance of, how much of the bar are we shifting? 1/6 L squared, because we're going from this point over to here. So hopefully you guys did the math on that. I want to make sure. Oh, that didn't work out. Come on, do what I'm. The whole thing, the whole works. Oh, fine. I'm just not going to do it then. So you had to, this, stop moving. This is 1/3, and the center is at 1/2, and the difference between 1/3 and 1/2 is 1/6. That's why I got 1/6. Just making sure. I gotta do math. So ml squared out here, 1/12 plus 1/36. 4/36, 1/9. So this is 1/9 ml squared. Moment of inertia. Good? Any question about that? That was part A. Fan-freaking-tastic. So mg, let's deal with h. How far has the center of mass descended? Yep. Yeah. So it's L/6. All right, that's the distance from my pivot point to my center of mass. It's still L/6. And that has to equal 1/2 times 1/9 ml squared omega squared. Goody. There's nothing. I can do this, cancel out and get a 3. I can get rid of the m's. I'm still looking at get rid of one of the l's. And it looks like I'm going to have, is that 9g over 3l or 3g over l? Is that right? I'm trying to do all the math in my head, but it's starting to hurt. So I'm going to assume that since nobody is stopping me, either you didn't do it or it's right. So I'll go with that. This is not the answer. This is the angular speed at the bottom. If I want the answer, I need to find the linear speed at the bottom. And the linear speed at the bottom comes from V equals omega times R. R has to be this distance, which is 2/3 L. Don't like this, but this is physics, so we must like it. 3g over L. Well, actually, you don't have to like it. Many of you do not. There. I would probably go ahead and square that, put it inside the radical, because I'm pretty confident when you do, some things are going to cancel. Yippers.
How did you know to what space for radius? And how did you know to use like 2/3
Instead of,
1/3
it asks for the bottom of the meter stick. So the bottom end. So that had to be whatever piece was that distance away from the pivot point. You're welcome. That all good? Want me to go further? Because this is not the answer. You should have, everybody's just looking at me like, I don't even know. I'll stop right here if we're going. So, okay, that's it. Yay. I don't even know who asked at this point. Oh, yay. Good? Excellent.